Hello everyone. Now we will discuss the interesting concept of the concentration of charge carriers and Fermi level in semiconductors. Before we proceed with the Fermi level in semiconductors, I will discuss about the concentration of electrons and holes in semiconductors. First, I will be taking the part A, that is concentration of electrons in conduction band. Why? Because electrons in semiconductors are free in the conduction band, unlike metals. Now, I will take the conduction band, that is the energy level above EC. I will take this band of energy, that is E2 E plus delta E. The concentration of electrons in this conduction band is nothing but dN into rho E dE. I hope you have seen the previous video that was in Fermi level and density of states in case of metals. Just to review that, just to recall, this rho E is called effective density of energy states in conduction band in case of semiconductors. What is the effective density of states? Effective density of states is what? The number of electrons per unit volume in this area and per unit energy in this area. I repeat, rho E is actual number of electrons per unit energy per unit volume. That is nothing but this rho E, and this is equal to Fe into Ne multiplied by dE. What is Fe? Fe is called Fermi-Dirac function. Fermi-Dirac function is nothing but probability. It is a probability function. Fermi-Dirac function is probability function which gives the probability of occupying an energy state by an electron. That is Fe. Ne is nothing but maximum possible density of states per unit volume. Density of states. What is maximum possible density of states? That is equal to the maximum number of electrons per unit energy per unit volume in this area. So now here for conduction band, you have to remember, for conduction band we define this Ne. That is what you need to remember directly. That is equal to gamma E minus EC. EC is what? Lowest energy level of the conduction band into 1 by 2. There is a condition. Condition is what? E must be greater than EC. That is, energy level must be greater than EC, means energy level must be in the conduction band. And what is Fermi level? That is Fermi-Dirac function. That is equal to, remember this, 1 by 1 plus e raised to power E minus EF by KT. That is your Fermi-Dirac function. But you can approximate it. Here Fermi level is somewhere in the band gap. So when E is much greater than EF, you can say, I am assuming, normally Fermi level is in the conduction band, in the band gap. We will see it later. So but I assume this is much greater than this. So for, I'll write it like this, for conduction band, that is what your assumption, E minus EF is much greater than KT. Why? Because E is much greater than, or E is much greater than EF. That is your assumption. So if E is much greater than EF, if it is much greater than this, so this will become large. I can neglect this. So Fe will be approximately equal to 1 by e raised to power E minus EF by KT, or I can rewrite it like this, e raised to power minus E minus EF by KT. Fine. So that is your Fermi-Dirac function for conduction band. So I can rewrite the concentration of electrons in the conduction band is equal to the Fermi-Dirac function and this the density of states. So that is gamma e raised to power gamma function into E minus EC power 1 by 2 into e raised to power what? E minus EF by KT. That's what you have. So that is your concentration of electrons in the conduction band. Now you can integrate it. Integrating, you will get what? You will get the concentration, that is n is equal to integration of this function gamma E minus EC 1 by 2 into e raised to power E minus EF, and you had negative sign, so there is a negative sign here, and into that is dE, that was to be there. So minus E in minus EF by KT into dE, that is your expression. But you need not to remember everything, but you need to remember the concentration integrating above. I'll not go for this integration because that will be lengthy. I'll be writing it directly, and what is you need to remember, the integrating you will be we get directly, that is mugging up n equal to NC, and I'm sorry, I need to write the limits as well. For conduction band, what is the range of this? That is from EC to infinity. Why? Because conduction band is varying from EC up to infinity. So that's what you have. So n will be equal to NC e raised to power minus EC minus EF by KT. This is important expression, and remember it directly. You should remember this expression. This derivation is useless. You don't have question on the derivation. There is rare possibility, least possibility, but this is important. You should remember this expression. Why? Because I'll be using this expression again and again. Where? And this comes after integration of this. You can try it yourself, but that will be simple wastage of time. So you should remember this expression. That was just to let you know how we arrive at this result. So here NC, that is known as, this is equal to, I'll write it like this, 2 into that expression is, you can just note it down, that is 2 pi mn kt divided by h square. So this is the expression. Is what do we call this? NC is called density of states in conduction band. We call this as density of states in conduction band, and I repeat, that is what? Density of states in conduction band, the number of electrons per unit volume per unit energy, that is density of states in conduction band. So I repeat, you should remember this expression of the concentration of electrons in the conduction band. So that is what you have in case of concentration of electrons in the conduction band. Now we will see the part 2, that is B part B, that is nothing but concentration of holes in the valence band. So that is the next topic we will discuss, concentration of holes in valence band. And remember the Fermi-Dirac function in for holes, I'll rewrite, that is equal to First of all, the concentration of holes dP is equal to Fermi-Dirac, that is rho E into dE, and rho E is what? Now it is important. Rho E is effective density of states in valence band, and that is nothing but number of holes in this case. Number of holes per unit volume per energy state, that is this, and this is equal to F dash E into NE into dE. What is this F dash E? F dash E is nothing but that is 1 minus Fe, and this is called probability of hole in the valence band. What is the probability of hole in the valence band? That is nothing but absence of electron. If an energy state in the valence band is not occupied by the electron, then that means that is a hole. The probability of occupying an energy state by an electron is Fe. So what is the probability of not occupying an energy state by electron? That is 1 minus Fe as per the probability theory. So that is probability of hole in valence band is nothing but 1 minus probability of electron in the valence band at that particular level. So 1 minus Fe as per the probability theory. So you should remember that is nothing but probability, or you can say Fermi-Dirac function of hole, and hole is always in valence band. So you get the concentration of holes is equal to 1 minus Fe multiplied by an E into dE. Now for valence band, you should remember for valence band the maximum density of states is given by gamma EV minus E, that is what you have, power 1 by 2, that is what you need to remember. So where E is less than EV, that is valence band. Fine. So and this is what you need to remember. There is no derivation for this. You should remember this. Gamma is a constant. What is gamma? I have explained in metals. Gamma is nothing but a constant, that is 6.42 into 10 to the power minus 27 approximately. I am not giving you the exact value, but just to let you know that is gamma is a constant. So here now let us see the Fermi-Dirac function. So Fermi-Dirac function for holes, that is 1 minus Fe is equal to what? 1 minus 1 by 1 plus e raised to power E minus Ef by kT, and you can rewrite it like this. If you simplify it, that is e raised to power E minus Ef by kT divided by 1 plus e raised to power E minus Ef by kT. That's what you have. Now I'll change the markers. So here important point, we are having valence band now. So for valence band, what do we have? E is much less than Ef. This is what I assume. So if E is much less than Ef, I'll rewrite it this equation like e raised to power minus E minus Ef, or I'll write it like this, Ef minus E by kT divided by 1 plus e raised to power minus Ef minus E by kT. I'll rewrite. So if it is much more than Ef, So this is much smaller than EF. This becomes very large. If this is very large, so this can be neglected. So in that case, 1 minus Fe can be approximated as e raised to power minus EF minus E by KT. That's what you have. So therefore, the concentration of electron holes in valence band can be written like this, that is gamma EF minus E, that is EV minus E into e raised to power minus EF minus E by KT into dE. Now you can integrate it. The concentration of holes in valence band will be equal to integration gamma EV minus E raised to power minus EF minus E by KT into dE. And again, just like previous case, that derivation is not that much important. You can, after integration, above integration gives what? Above integration gives, and this is what you remember, I told you just need to mug it up. You don't need to go for the complete integration. That is P equal to NV e raised to power minus EF minus EV by KT. That is what you need to remember. This is very important expression. Why? Because complete Fermi level can be remembered for both type of semiconductors if you remember these two equations. So here, what is NV? NV is equal to 2 into 2 pi MP by h square into that is what? KT and power 3 by 2. What is MP? MP is effective mass of hole, and in previous case I did not tell, Mn is effective mass of electron. Normally, remember, normally, I won't say always, normally we take Mn equal to Mp, but that is not true in all the cases. Fine. NV is called density of states in valence band. That is called density of states in valence band. So this is the concentration of holes in the valence band. So just to revise whatever we have done. So you should remember the important points from this topic. Important points. What you remember, what you need to remember. N is equal to what? Nc e raised to power minus EC minus EF by KT, and P is equal to NV e raised to power minus EF minus EV by KT. These are very important expressions. You should remember. NC is what? You need not remember as such as far as exam is concerned. Just to recall, 2 into 2 pi Mn KT by h square whole 3 by 2. What is NV? 2 pi MP KT by h square power 3 by 2. This is density of states in the conduction band, and with density of states in valence band. That is what you have. Now here, this is what you need to remember, but let us see how to derive the relationship between N and P. As per law of, I'll make a heading. Heading is what? Intrinsic carrier concentration. Intrinsic That is third part. I have discussed two parts: concentration of electrons in valence band, concentration of holes in concentration of electrons in conduction band, concentration of holes in valence band, and third is intrinsic carrier, that is intrinsic carrier concentration. And we know, as per law of mass action, what do we have? As per law of mass action, N into P is equal to what? Ni square. So this gives what? Ni square, multiply these two equations, that is Nc into Nv e raised to power, you can simply add all these, so minus Ec minus Ef plus Ef minus Ev by Kt, that's what you have. So this gives Ni square is equal to, now this is Nc Nv e raised to power minus Ec minus Ev by Kt, or this gives Ni square is equal to Nc Nv e raised to power minus Ec minus Ev is what? That is band gap of the semiconductor, that is what you have. This can be written further like this: Ni is equal to under root Nc Nv into e raised to power minus the band gap by 2 Kt. That is another important relationship, where what is Eg? That is band gap is equal to Ec minus Ev, and that is, I repeat, that is band gap or forbidden gap of the semiconductor, that is intrinsic carrier concentration. This is important, and these two, whatever you have discussed till now, these are the important expression as far as exam is concerned. I repeat, this topic is very important for engineering services prelims or maybe mains, but not that much important for gate. But there are a lot of questions in engineering services prelims from this, in electrical and electronics both. Now let us go for the next topic under this heading only, that is Fermi level in intrinsic semiconductors. Fermi level in intrinsic semiconductors. Let us draw the expression. First of all, I will draw the diagram. This is valence band, this is conduction band, and this is lowest level of valence band, this is highest level of conduction band. Now, for intrinsic semiconductors, what is there? N is equal to P. Concentration of electrons in the conduction band is the same as concentration of holes in the valence band. So this gives what? Nc e raised to power minus Ec minus Ef by Kt is equal to Nv e raised to power minus Ev minus, that is Ef minus Ev by Kt. So what do we get? This gives e raised to power minus Ec minus Ef. If you take this on this side, this will be again minus that is plus Ef minus Ev and whole divided by Kt. This is equal to Nv by Nc, or this gives what? you can take it this on that side, that you can take log on both sides, natural log on both sides, minus EC, then plus 2EF minus EV is equal to natural log of NV by NC, or this gives EF is equal to EC plus EV by 2, and I'm sorry, KT as well here, plus KT by 2 ln NV by NC. This is very important expression. There was question in GATE on this relationship this year, or maybe I don't remember the year exactly, but this was the expression where there was one question, a 1 mark question on GATE. So you should remember the expression. Now let us see. I told, if you remember, if effective mass of electron is same as effective mass of hole, that is what we discussed, then what? NV is equal to, or NC is equal to NV. We have seen the expression of NC and NV. If effective masses are same, then both will be equal. In that case, EC will be equal to what? EF will be equal to what? EC plus EV divided by 2. So the Fermi level will be at the center of the energy gap, that is Fermi level, and EC plus EV by 2 means what? If you see this, from here to here it is band gap, from here to here it is half of the band gap. So I can rewrite this like this. EF can also be written like this, that is lowest level of valence band plus half of the band gap, or this can also be written like this, EF is equal to highest level of conduction band minus half of the band gap. These are some of the expressions you should remember. The Fermi level in intrinsic semiconductors is at the center of the energy gap if this condition is fulfilled. If effective mass of electron is same as effective mass of hole, that is the condition. I hope you will remember. And there is interesting point to be observed. If effective mass of electron is same as effective mass of hole, Fermi level in intrinsic semiconductors is not affected by the temperature. It is totally independent of temperature. But if effective mass is not same, then you have just seen the previous expression, the Fermi level will shift even in intrinsic semiconductors if this condition is not fulfilled, if this condition is not satisfied. I hope this topic is clear to you, how to derive the expression of Fermi level in case of intrinsic semiconductors. That can be one conventional question in engineering services mains, or objective type question in engineering services prelims. GATE, there can be 1 mark question, of course. So this is now next topic we will see the Fermi level in extrinsic semiconductors, that is N type and P type materials.